Hello and welcome viewers. So hope you're all doing fine and having a great day. So myself Archishman, I am a first year undergrad student at Jadavpur University. So I'd be helping you out with the calculus portion, at least differential calculus like limits, continuity and differentiability and so on. So let's hope have fun and let's see what happens next. Till then we'll continue with this limits portion today. Okay, so let's start. So before I start talking about calculus and discussing and having fun with maths, so before I start I want to say I'm thinking of breaking limits in two portions, that the two video will come out about limits. First video which I am making now, so it would be more on a bit of series. So we'll talk more about sequences and series and basically the notion of calculus. So that is very important. So we all know that's calculus. If we can master calculus, we can really master a lot of mathematics. So yeah, so now we are going to discuss about notions of calculus. We're familiarizing with calculus, so that's the basic and very important part we want to learn. Okay, so nice. And then we're moving on to functions, that is limit of functions. And yes, then we'll be solving more on problems, like as we do on our educational platform. We'll be solving more and more problems on limits of functions and all that. Before that, we'll be doing this, and that doesn't mean we won't solve problem. Yes, we will solve problem, lot of problems, but not like in the second video. Second video is basically problem solving. So today, believe me, it's gonna be fun. You're gonna love this thing, I bet. Okay. So limits, basically you can say limits is actually real analysis, what we are going to learn now. That is basically real analysis, and yeah, you can say also calculus, no problem in that. So what is calculus and how it arose? So I'm not going to tell all the history about, even I don't know, so I'm not going to exploring that historical part of calculus, how it arose from Newton and all that. But why was calculus required? What was even the need of calculus? Maths was going fun and we know everything, so there was abstract algebra and everything. So let's just see. So people like to have the sum of the series like this. So maybe they don't even know what was a series, but they like to calculate all this. They had fun back then. It's a long time ago. So they had fun doing all this. So if we want to calculate the sum of this series, so if this is a finite thing, we always know that it's, so we have calculated in previous classes. We all know that's it, in 10 plus 1 by 2. So if there is a finite thing like say 10, we're gonna end up like, so the sum would be 55. But problem arises when we say this sum goes on and how much. Now that's another story. That is the interesting part of this calculus process. So this sum goes on, so we don't know what is the sum of this sum. If this goes on, how much would be the sum. One more fun thing is having a series like this. So let's give it a try. When you are ready, please come back, pause the video till then. Okay, hope you have all given it a try, and these all are doing fun, nothing more. So don't just waste much time. I'm just creating a notion of calculus, making just familiarize calculus with all of you. So suppose say we take this sum in this way, okay, and this way. So every term, every basis gives us 0. That's right. There's no problem in that. So we just adding zeros and all over again zeros. So what we get is 0. So there's a no-brainer. So we always end up with 0. So I'm again writing the series. Now let's just say we leave this one here. We don't take it in our consideration. We just take braces and continue like this. So these all are continuing now. So I'm interested to take this series in this form, and this one is left over. So what we get a 0 here, a 0 here, and all 0 as same as this. So basically this thing over is the same thing over here. So we get a 0. So this ends up in a 0, but we have a 1 left over, so we get a sum 1. Now see the magic. The same series gives us a result 1 as well as a sum 0. So how even on earth how that could be possible? So that isn't actually. So that's why we are learning calculus. So we want to explore why these things happen, and we're not just gonna deep dive into these series and all. So this is a vast portion. I mentioned I want you don't just deep dive into these things, because these are a lot of things. There are a lot of things in real analysis. Let's restrict ourselves into the limits that covers our JE and Wbjee portion. Okay. So basically, what is the limit? So we talk about sequences. Now say there is a sequence. Suppose say xn. So xn is a sequence and n is the index here. So suppose say xn is a sequence like this one. So we have a sequence like this. 3.1 and then 3.12 and then 3.13 and then 3.138 3.1389 and this. So what intuition tells us that this thing gonna end up after infinitely many terms to 3.14. So that is our limit now. So just intuitively we understood that it might after some point it might be very close to 3.14, and that it's gonna be the limit of this sequence. So we just intuitively understood that this limit of this sequence is 3.14, though we don't know what is limit now till now. So how do you just get a intuition of limit? So limit is nothing. You just see these numbers are approaching. Now what do we mean by approaching? So suppose say let's say we have a number line. Now this is some real number a, and this is something maybe a minus h, and this may be a plus h, where h is also a real number. So let's take a variable x. So when we say x approaches a, that is we denote x approaches a by this sign, which we call x tends to a. So let's try to understand it very clearly. So we say x tends to a when for all epsilon greater than 0. That is, there is a number, you give me a epsilon which is positive. So you know this is for all. This is the set theory notations I just want to mention. This means for all, and this means there exist. Don't just worry seeing these set theory notations. You'll all get used up to this. Just remember this. That's not very tough, I think. So there exists. Okay, so where was I? For all epsilon positive there exists okay, this does not get up with the sequence definition. So if you give me a, so for all epsilon greater than 0, if we can say that mod of x minus a is less than epsilon, then we can say that, so then we can say that x tends to a, right? So you know, epsilon, the main thing to note here is epsilon. So this is mod is nothing but the difference. So you can take epsilon, say I said 1, so maybe there's a gap of 1, and so that works, that very well works. So let's say your x varies here, let's say you give me a x which always varies in this portion. So when I say x approaches a, you said me okay it is epsilon equals 1, so very in very well manner it will check that my x will always approaching a, because you put epsilon equals 1 and my x is here, so there is no problem in that. But not only 1, this epsilon should work for all values greater than 0. So to check if x approaches a or not, we have to make epsilon smaller and smaller till, I mean very small. Let's just make this very small. Epsilon needs to be very small. So if you want to check x is approaching a or not, you need to take epsilon very small, like 0.0000. How many zeros you can take? There's no problem in that. Like something like that. So you can just you can check with all these values, like if that x approaches a or not. But these aren't enough. This process isn't enough, because this process is finite and we won't get a number which is absolutely small. Like there doesn't exist any number smaller than that. There isn't any number like that. So we'll always be cutting that number. We'll always get a smaller number than that. So that is not the right approach. You can always check, but that's not the right approach. So what I am trying to say here, that if you give me an epsilon greater than 0, which is greater than 0, but it could be any epsilon, it works for any epsilon. Okay, so even if you can't think of an epsilon which is much smaller, that should even work for that x. So when will that work? That is the question. So suppose say this is again, now we have an interval like this. So you say my x varies over this interval. Let's say this is h. Okay. So if you give me a epsilon less than h or less than equal h, so this x would always fit. But I say again, take some smaller. Let's say some delta. Now delta is very small. You can, that is delta is so much small that you can't even imagine. So I said that would even work. If that works, then we would say x is tends to a, x is approaching a. If that doesn't work, then we would say no, x is not approaching a. Like I can give an example, like so you can understand very well. So an example would be, suppose say we have a sequence like this one. Suppose this is 1.1, 1.01 and 1.001, 1.001, and in the meantime I put, so this continues on, and then I change this sequence and I put like this. Why am I doing this? So you see there are many terms in between this. I am not interested in those, but I can see like that this sequence isn't approaching any number. If you said that would approaching 1, let's say I'm saying that the sequence approaches 1, but then someone would again gonna say that it's approaching 1.222 and it's also approaching 1.3, so that isn't correct, right? So but here one thing I'm going to mention, if I had a series like this one, and the number of zeros are increasing after each term, so there are 3, in the next term will be 4 and 5, so what that would be approaching. So is this sequence has a finite limit? Is this sequence approaching some particular number? Okay, in this case we would ignore these numbers. Finite numbers don't actually matter in these sequences and series. What we are interested about is the infinite numbers, infinite sequence, what the limit of that infinite sequence is. So in this case, yes, it's approaching 1. There's nothing wrong in that. We can say x is approaching 1. That's correct. So I think you have got I would say a much better idea about what I am trying to say. What is an approach? How do a variable approach a finite number? So up to now we are in the finite numbers. So till then it was x and a was belonging to some real number. Now there is a bigger concept which I am trying to say. So what we mean, when we say x tends to infinite or x tends to minus infinite. Look, this particular idea is very complex and as well as very simple and simultaneously. So I'm gonna take up the simple thing, and I'm gonna just tell about simply what is this thing, so you can understand. And yes, it's a very much complex thing, and we are not going to discuss those things here. So keeping it simple, I would say what x approaches infinity mean. So if I say something approaches infinity, first you have to know what is actually infinity. So infinite, is this a number? No. It isn't a finite number, it's just a concept. So infinity is nothing but a concept. So by infinity, I mean this thing is larger than anything I can imagine. So it's a concept, right? This is nothing, not any number, like you would say that that's 1 crore, 1 billion, 10 billion, 100 billion. Even 100 billion is very small compared to infinite. Infinite has no match in finite numbers. So infinite is bigger than anything you can tell of. You can, simply speaking, this is the thing. So when I say x approaches infinity, let's just move with the positive infinite. So when we say x approaches infinite, I want to tell that x is greater than any n you give me. So x is any x is greater than m, x is greater than any real m. So you give me any m, I can give you x which is always be greater than m. So that is by this we mean x is approaching infinite. So x has no bound, x is unbounded. So x is moving unboundedly. So finally it crosses every finite numbers. It crosses every big finite number, every billion finite numbers. So there is no boundary, or so x is actually unbounded, and that's when we call x is, if that's in the positive portion, we can say x is approaching infinite, and if that's in the negative side, we can say x is approaching negative infinity. Okay, so I hope you got some clear ideas. Now just we'll be solving some problems to understand, to get a better picture, to get a better view of this thing. Okay, now tell me, so one thing I would warn you about, when you write like this, suppose you writing this thing, say infinite. So you wrote s. Now keep in mind this s is a series of infinite terms, or we can say it's an infinite series, right? So always keep in mind this thing. There are many pitfalls in this thing. When people just take this is an infinite series, as we can see, and sometimes they forget this and they take s as finite. So that would be very mistaken. That is not a right thing. You should always keep those both sides in mind. So you can just think. Now I'm telling, suppose we have a series like this. You might know about this series. So basically, what is this? Basically, this is n equals 1 to infinite. So could you just tell me what is the value of this series? Take your time, and when you're done, just come. So hope you all have given it a good try, and now just say what is the value of this series. Okay, so this you can see, just these terms are decreasing, right? These terms are decreasing. So you might think that okay, that those terms are decreasing, it must be finite, but it is not. This series is infinite. So let's just see how it is infinite. So we have s on one side. This is this. It goes on to infinite. So how could we guarantee that this thing is not finite? Let's just take this thing. So we are doing an inequality here. So see. So what we have here is 1 plus r. Okay, we write these first two terms as it is, and then there's the trick here. So you need to be tricky in doing this series. Always be tricky. Always try to trick those series, so that you can just give a bound, some upper bound or lower bound. You can just bound the series. If you can bound the series, that's very well. But if you can't, just look. There is no limit of that series. So I can take these two terms. So I can just write. Isn't it correct? Oh, sorry. It should be 1/4. So 1/3 is greater than 1/4. There's no wrong in that. And 1/4, okay, so no problem. You can just give equal somewhere. Yes. Okay. So we take these two terms and then we take these four terms. So these are 1/4. And so what should be the number in these braces? See, the lowest number in this brace or bracket, first bracket, is 1/8. So if I'm gonna say that these all are greater than the right hand side, so we must take 1/8 on the right side as well. So I'm taking 1/8 4 times and so on. So the next braces will contain 8 terms, each including, so there will be 116 8 times, 8 times and so on. There will be then next will be 1/32 taken 16 times and all. So what will be getting here? So all braces are giving us half, right? So I just take this, say, n times. I'm not saying n is finite or infinite. I'm not just arguing about that. I'm just taking n times. So this is 1/1 plus n over 2. So is this thing finite now? Can you tell me? Yes, it is finite if n is finite. Now if as we increase n, this thing is going to increase, and we see that we change nothing here. We can take as many as terms we like in this series. In this series called, actually it is known as the harmonic series. This is a very famous series. This is known as harmonic series. It will be used here and there in mathematics. See, this is harmonic series, and we can take as many terms as we want. So we can take n 100. So this would get a value. So if we increase n, this has no bound. Again we get an n. So if you give me an n, I can always take as many as terms in this series so as to exceed n. So there is no finite n which can stop this series. So this series is gonna increase and increase, so on. See, it will never stop. So it isn't this is not a finite series, and hence we can say, since it has no bound, it is increasing. Since S has no bounds, I would say upper bound, and S is increasing, S tends to infinite as our terms n goes to infinite. So we can say, okay, so we already know 0 greater than S, 0 less than S, we already know that fact. And so S is approaching infinity as we increase our number of terms, as we take infinitely many terms. So we can see that. Moving on, we have one more important series, that is, this is famously known as the P series, not the T series that we watch in YouTube, not the T series music channel. This is P series. This is very serious. So what is actually P series? P series. So P series is like this. 1 to infinite 1 over n power p. So you all are familiar with this version. This is summation. You already just did it. So this is a summation. We know what this means. This is basically 1 over on. So this is actually known as the T series. Now what I am going to do with this and how is it of our interest, I am going to tell you. So just look at this series. We say it is S2. So this is S2. When it is S2, we take P as P equals to 2. P equals 2 in this case. So what do you think? This series has a finite value or not? So just give it a try, and when you're ready, come back. Okay, so I think you have all given it a try, and after that you have paused the video and come here to see what this actually series has gone. If you are right about, then that's very great. If you haven't got it right, okay, we'll explore, have fun. So we are here to have fun. So there's nothing to worry about that. This series is maybe new to you, not to worry about that much. So again we do this thing. So since actually this is a very large topic, so I am telling this thing has a finite limit. So how could we do that? Suppose say this thing. And then we're gonna take 3, 4 square, 5 square, 6 square, all that are smaller, and all that are smaller than 1 by 2, that is 1 by 8. Sorry, all that are smaller than 1 over 2 square. And then we take 1 over 2/4 4 times. Basically the same thing we did with the harmonic series, just that opposite way. So we now know the pattern, and what we are gonna get is something like this. Let me just no problem in that. This is half, we have 1 square, 1/3, so this is a GP, right? This goes on and on. So this is a GP, geometry progression. So we know this GP very well. This is nothing but so what is the value of this GP? Calculate it. So we are gonna see this GP has got a value of 2. If we calculate, we are gonna end up with the value of 2. This GP has got a finite value. So what we get is 2, that is 5 by 2. So we have just given a bound to the S2. So we now know that S2 is bounded by some number, some m. I would say this isn't a perfect match for the bound. This isn't the closest bound we could have ever put, but this is a bound. So we have got a bound. We know that S2 is smaller than some finite number, and obviously this is greater than 0. So this has got some finite value. And what is that finite value? So for your interest, I am saying S2, this value of S2 is pi square over 6. That's very interesting. If you are really enthusiast about these things, you can check the YouTube channel called 3 Blue 1 Wrong. They've all I think they have all covered these things, or might be in some later videos I'll be doing these things. So let's just hope well. And okay, now we'll be speaking to our topics.